So this section is really easy. All you need to know is that you can use the tree diagram for most of the things. So for example here, you toss a coin 3 times, so you can have heads, tails in the second toss, heads, tails, and then for the final and third toss you'll have heads, tails, and so on. This helps you first of all know the events. Like when you know the events, you can immediately look for the possibilities. So for example, let's solve them together. This is the sample space, by the way. Heads, tails, and so on. First toss lands heads, so all of this basically. At least one of the tosses lands heads, so at least one. The only exception, if you can see it quickly, is tails, so you can do one man stack. So basically everything but tails. Everything but tails. Anyways, at least one of the tosses lands heads and the second toss lands tails. Let's do the second toss because it's not at least, and you can immediately look at it. So second toss lands tails. So this one and this one. Yeah, this one and this one, second toss. So we must have a branch here because this has heads as second. This also has heads as second, so we don't want it. So this branch is immediately, let's double check. At least one heads, we have heads here. We're safe. The entire branch is safe. Here we don't have first heads, so we must look. Here we have heads, here we don't have heads. So, anyways, that was weird. Anyways, I don't know if you guys heard it. There was like a beep sound. Anyways, so we need at least one heads, so that'll be tails, heads. And the rest, this one you don't have it because it's wrong. So you have 3 events, or you have 3 possibilities. Heads, tails, heads, tails, and tails, heads. So yeah, it's really easy with a tree diagram rather than writing the set out. A 4-sided die, and if the number is even, you roll it once again. So 1, 2, 3, 4. 2 will be rolled again. So 1, 2, 3, 4. 1, 2, 3, 4. That's your sample space. You just write out, I guess, 1, 2, 1, 2, 2, 2, 3, 2, 4, 3, 4, 1, 4, 2, 4, 3, 4, 4, and that'll be the end of the section. So for this one, it's really easy. You just have your tree diagram. You can also draw it like in the beginning of the exam for 3 coin toss, because you can use it for a 3 coin toss, for a 2 coin toss, and 1 coin. I don't think you even need a tree diagram, but it's always there for you. And you can do it also for a dice roll for a 4, 1, or a 6. So 1, 2, 3, 4, 5, 6. 2 rolls. You basically can do it for anything, and have it just ready. You can do pretty much race through the exam because you already have the thing right in front of you. So here you'll immediately know prime numbers. You have 2, 3, 5, and you have a probability of 3 over 6, so that'll be half. If you want, I'll write them down. So 2, 3, 5, and you have probability of half because it's 3 over 6. Cardinality, by the way, is the number of events in a set or so, or the number of elements in an event or so. So cardinality of prime is 3 because it's 2, 3, 5. There are 3 elements, so cardinality is 3. Cardinality of an event over cardinality of I was going to say superset. Cardinality of sample space is going to give you the probability. That's just the formal way of doing things, if you ever come across them in university or something. Anyways, odd prime number is just omit 3, so 3, 5, and that'll be 1 over 3, a third, because it's 2 over 6, so a third. 3 tosses are similar. Again, do your tree diagram. For me, I'm just going to do it quickly. I don't even have to confirm it because the idea is use the tree diagram. So 3 tosses are similar means they're the same. So heads, tails. Probability is it's 2 to the 3, so 8. That's the number of events. 2 over 8, so it'll be 1 over 4. At least 2 heads appear, so heads, tails, heads, tails, heads, and tails. No, heads, tails. Yeah. Anyways, when you have your tree diagram, you can immediately do it. For me, drawing the tree diagram is going to take time, so I'm just going to do it mentally. For some parts, I don't necessarily need to do it. It's 1 over 2 because it's 4 over 8. At least 2 heads are observed after this one. The only thing I want to emphasize on is that what I thought when I read this is I immediately thought of heads because it's a first toss heads, and at least 2 heads are observed after observing that heads. So I thought of 2, after it. But no, it's actually, the wording can be tricky. It's actually locked to be heads at the beginning, but heads can be here or heads can be after it. So basically, it can either be this and an empty one, it could be heads, tails, or a heads that's locked like this, locked, and it can be tails, but here can be, no, it must be heads. So this is why the cardinality of this, it can be either heads, 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 or heads, heads, tails. This one must be heads, tails, heads, because if this changes to tails, you have 1 heads. So this is not satisfied. So your cardinality is 3/8. 1, which is heads, 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 and 2 heads, heads, tails, and heads, tails, heads. This also, by the way, the technique I just did here helps with probability for the other ones, for the combination and stuff. Like you lock something, I usually draw a circle around it, and anything I need to check, like I can confirm, I can draw it like this. So it could be this, or it could be this. It helps with other parts, which I might be touching with you guys in this chapter. Anyways, so here, 4-sided die, 2 numbers of opposite parity. Parity means odd even. Opposite parity, so means 1, 2, 1, 4. So odd, even, odd, 2, 3, 2, 1. So it'll be half because they're divided evenly. So there are an even number of odd numbers and an even number of even numbers. So it's half. The sum of 9 appears. In a 4-sided die, rolling twice, maximum is 8. So this is 0. Probability is 0, it's impossible and it won't not happen. Result if a second roll is larger than the first, you can have the second larger than the first, right? So 1, 1 is not an option because you want the second one to be larger. So 1, 2, 1, 3, 1, 4, 2, 3, immediately skipping, 2, 3, 2, 4, and 3, 4. And that will be 1, 2, 3, 4, 5, 6. 6 over how many? Well, we're rolling 4 times, so 16, 4 squared. And so it will be 3/8 probability. And so yeah, are there anything? No. So yeah. So for this one, I'm just going to be doing some of them because the rest are just drilling, repeats and stuff. You can do them for practice. So for this one, just if it helps, if you don't want to draw all 26 or 36 actually, 6 squared, so 36 possibilities, it's easier just to see that it's 2 odd numbers together. So 1, 3, 5. So what are the possibilities? There are 9. There is you have 1, 1, 1, 3, 1, 5, 3, 1, 3, 5, 3, 3, 5, 1, 5, 3, and 5, 5. So there are 9, 3, 3, 3 possibilities. So 9. So immediately solve it without having to draw it. This one you can do the complement in your head, so or write it down, but like you can do it quickly. So 1 or more. This is a nice one because when you have 1 or more, in other words, at least. If you're confused, as in, do you include the one, do you not, or like in your head, sometimes you get confused. It happens to me. So I usually like draw something like 1 or more. So it could be 1, 2, 3, and so on. So 0 is not applicable. So I take the complement, which is 0. So 1 minus that is the 0. So 0 tails means heads, 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 heads in a 4 toss. So anything but that. And you just keep listing. There are 15 of them. You want probability? You don't need to even consider it. It's 15/16. No need to even list them. I mean, if they ask you to list, you can list, but they only need probability. This one always gets me because I don't play this card game specifically, but what you need to know is that there are 26 red cards, there are 26 black cards, there are 4 aces in the entire set of 52 cards. 4 of those aces can either be a red ace, 2 of those, and 2 of those can be a black ace. So how many cards do you have? 52. Of those 52, there are 26 red, 26 black. Of those 52, there are 4 aces. 2 of those aces are red, 2 of those aces are black. So you have this 26 actually is 24 black cards that are not aces, and 2 of those are black aces. This is how it makes 26. So this is how we can see it as an intersection. If you want as a Venn diagram, I could attempt to draw a Venn diagram. This will be black, this will be red. There is actually no intersection, to be frank with you, there is no intersection. They don't intersect because you cannot have a black-red card you know, no way. So red, black. What happens to be an intersection though is aces. Actually, an ace can either be red or black. So it's pretty much like this. Ace, ace. So it's a subset more like of. So you can have here 2, here 2, here 24, 24. So 26 total, 26 total. Total is 52. Anyways, a red card, there are 26 red cards, so 26 out of 52. An ace, there are 2, so there are 4 aces in a 52. So 4 over 52, 4 over 52, which is 1 over 13, and this is half. A red ace, you can multiply those, half times this, which is 1 over 26, or you can just see here, a red ace, there are 2 over in a 26, so 2 over 52, because always divide by the sample space, so 2 over 52, so it'll be 1 over 26. A red card or an ace, this is where you need to consider intersections. A red card is all of this, so 26, or ace is 2 or 2 here, so what you can actually do is 24 plus 2 plus 2 over 52. Let me show you. 24 plus 4 plus 2, because 24 plus 2 plus 2 is satisfying the condition, over 52, which if you add them up, just to show you that they'll be equal to whatever you had in mind before solving this exercise. I think I did a slight mistake. Yeah, 2, sorry, not 4. Yeah, so it'll be 24 plus 2 plus 2 over 52, which will be 7 over 13, which you can do in a different way, just red card, so all of this, or an ace, plus 4, so basically, red card probability half, plus an ace probability is 1 over 13, minus intersection, which is red or ace, so 1 over 26, which will also, you'll get 7 over 13. A red ace, but it's easier to see here, by the way, a red ace or a black card, and a red ace, so 2, and a black card, so 26, so it's 28 over 52, so 7 over 13 also for this one. Anyways, this one also just Venn diagram, and don't need to do it, just to show you AB. Music, art, and outside, by the way, you know, some people don't do either, you know, they do neither, so you need an outside set, just to consider the neither. So music, you have 16 here, so 16 here inside, 12 inside, 8 take both, that's how we can solve now. 16 minus 8 is 8, 12 minus 8 is 4, 8 plus 8 is 16, yeah, and plus 4 is 20. We have 24 students, so there are 4 outside. Double check, 20, yeah, 20, 24, yeah, 4 outside. So 4 outside, 8 here, 8 there, and 4 here. So student take music and art, 8 plus 8 plus 4. No, sorry, and art, yeah, 8, only 8. 8 over 24. Takes music or art, this is the one where you add 8 plus 8 plus 4, or if you do it casually normal way, is 16 plus 12 minus intersection, which is 8. Same thing. A student takes music but doesn't take art, takes music but doesn't take art, so 8. So again, the Venn diagram helps. If they ask you, doesn't take either, you can just add these two up. Takes art, takes music, and minus this, minus that, like 24 minus. Anyways, but a Venn diagram always helps. This one, all you need to know is if you get confused, you don't need to memorize any rule like A union B complement. Is it A complement intersection B complement? Is it? You don't need to really memorize anything. It doesn't even save your time, because if you make one mistake, you could just be like, you know, frozen in place. Do I do this? Do I do that? I forgot which. So let me show you how you can prove anything, any of those. So A and B, we're back to the simplest, A and B and an external set. So A intersection B is this area. A union B is this area. A complement intersection B complement, for example. Complement is anything outside. So A complement is all of this, you know, all of this, anything but this. And B complement is anything outside. So the intersection will just be anything that's outside. And this is actually indeed equal to A union B complement, because I saw that because over time I started noticing that A union B is this, complement of those is outside, so you'll see the same. This is why there is an actual rule out there that says A complement intersection B complement, you flip the sign, so B union, and complement outside. So it's basically the same idea as this actually also is in computer science, is when you do A or B and you have like a not outside or something, when you insert that, it'll be A not or, I forgot the or sign in computer science, but anyways, or, I'm just gonna do like or, not B. Anyways, but the idea is similar, basically. The idea is a bit similar. There is a rule outside, but you don't need to know that rule. Maybe for computer science it's harder to see, but now that you make the comparison, for those of you who are taking computer science later, now you get like a better idea. So just have a Venn diagram there. And you can basically solve any of those. It won't matter whatever exercise they give you. Just think of the complement as outside. A union B, anything inside, outside of that is anything outside of both sets. A intersection B complement is A here, B there, B complements anything outside, A is here, so anything that's outside of B but inside of A. So just A from here, not the intersection. Anyways, so yeah, pretty much anything can be solved using a Venn diagram. Okay, so for this one, it's probability of A given B. So it's probability of A intersection B over probability of B. B being the given. So anything here given, it's probability of that. How do you prove this? How do you get this? If you don't understand this, if you need to know, because it's always nicer to know, especially if you go to university. For those who are doing finance, will probably be doing statistics, and those who already it's finance and statistics, it'll be really like nice to know about the probability, because you're gonna be stuck with it most of the time. So yeah, so here it's gonna be heads, tails, heads, tails. Also, by the way, statistics is like a really strong major. My sister does biomedical and she's doing statistics. She did statistics first year, I guess. I mean, first year is really general, but some people like will carry with it, even though it's not as relevant. Same with programming. Anyway, so here to explain the given and like what it means to be given something, like knowing something has happened. For example, knowing that there is rain. I tell you now, right now, I tell you it will rain. I tell you the probability that the pizza will arrive, knowing that it will rain. I will tell you it will rain. So what will be the probability that the pizza man will arrive? Basically, it'll be the probability of it raining and him arriving over it just raining. But how do you see that? Well, since it's hard to talk about forecasting, let's talk about something we can confirm for sure, which is a coin toss. So for a 3-coin toss, because the complexer, you know, the more complex the better, but of course not too complex, just to show you that even when it's hard, like when I tell you a question, you might freeze. Probability of tails, given that second toss is heads, you'll be like, that question looks ugly, you know, it's like, it's hard. But let's break it together one step by step. I can tell you immediately the answer is 3/4. But how do you do that? Second is heads. This is heads. This is heads. The second being heads is only these, basically the entire branch, by the way, but it's just that it's, I guess, nicer to draw from here, because this is confirmed because we have walked down here, so this is definitely included. But like, this is what we have to make a decision. Do we include this or both of them, or neither of them? Same thing here. We only care about heads, so this entire branch is not included, this is not included. So we can erase it actually if you want. We can erase it. Like this and like that. And so we only need these branches. Knowing, by the way, this is 2 possibilities, there are 2 possibilities here if you want to include them. This is 2, 2, this is how all of them is 8. 2 to the 3 basically. Yeah, anyways. So probability of tails inside of those, given, knowing. So you cannot tell me heads, tails. I'll immediately pause you before even continuing the third one, but I never told you that the second one is tails. It'll be always heads. So knowing that it's heads, probability that it's tails is at least 1 basically. If there is a tail here, if there's a tails within it, at least there's inside the tail, this is possible. This is impossible because there's 0 tails, so you don't include it. Here there's a tails here, so you immediately include the entire branch. Tails, heads, heads, tails, heads, tails. has a tails. So its probability is 3 out of 1, 2, 3, 4, 3, 4. So 3 over 4. Another way to prove it is using this formula. Now that we can use it, is probability of A intersection B, probability of basically tails and second head toss, which is 3 over 8 over probability of B, which is probability of second being heads. So 1, 2, 1, 2, so 4 over 8. If you do the math, the 8s will cancel, so you end up actually, you'll end up with 3 over 4. So yeah, pretty much, this is how you do it. And this is all you need to know, because all of those will just follow the same idea, that is probability of A intersection B over probability of B. And you just need to get to know, like, for example, the complement. Let's do this together. Probability of A complement intersection B. You want to think of it like this: A, B. A complements anything outside of B. And it's probability of A complement intersection B, probability of B. So what is probability of A complement intersection B? It's this inside, because this is all of it the complement, including outside, but it's inside intersection B, so it'll be this. So this area over probability of this. So if are we given numbers? Yeah, we're given numbers. So probability of A, and we're given probability of A and B, and the intersection. The union. So we just subtract. We get the intersection. Probability of B minus intersection will be this. So it'll be 0.9 minus 0.6 it'll be 0.6 plus 0.75 minus 0.9, which will be, where's my calculator? Oh, wow, it's not here. Anyways, you just add them up, so 0.6, 0.75, so 1.35 minus 0.9, so 0.45. This will be the intersection, so here's 0.45, so 0.75 B minus the intersection 0.45, it'll be 0.3. So there's 0.3 here, so 0.3 over probability of B being 0.75, and you just calculate. Anyways, it doesn't matter if my calculations are right or wrong, but the method is definitely right. The thinking is definitely right. You can do anything with complements. You use the Venn diagram and you use the logic you have with the formula. Probability of A intersection B over probability of B, or equal to probability of A given B. That's how it is. So all of this is basically done. Same thing here, the probabilities, it's 0.3, 0.2, 0.8, no, 0.08, and yeah, just do Venn diagrams for those. So for this one, it's just that all you need to know is just you can use this. So it's easier because you can put slots here, you can put anything you want. What could possibilities there, 7 possibilities, 6 possibilities, whatever, and multiply them, add them. It helps you visualize the possibilities. Here you have 4 math books, 3 chemistry books, 6 biology books. How many ways can a student choose a book? You can choose a math book, a chemistry book, a biology book. Keeping in mind all the books are different, by the way, because you can choose an AS math book, an A-level math book, your grade 8 math book, any kind of math book that are different, by the way, these are different. Chemistry books, your last year's chemistry book, today's chemistry book, if you, not today, this year's chemistry book if you're doing A-level or AP or anything. Biology, if you're doing A-level, AP, previous year's books, HSE, and any personal book, or a writer that has written something, anything. So a book, it can be either this, or, pay attention to my words, or a chemistry book, or a biology book. So plus, or in statistics means plus. So 4 plus 3 plus 6, which is 13. 4 plus 6, and so on. So one book of each kind. So you need a book from each kind. So you need a math book and a chemistry book and a biology book. So you need 4 times 3 times 6. You can have these many possibilities, which is 24 times 3, which is, it's unnecessary to calculate, but yeah. You need one from each, a starter, an entrée or an entry, dessert. What's wrong with me? I have to switch to French. Or half German, half French. It's stuck. Anyways, so you just multiply them. So 4 times 6 times 3, because you need one of each. 6-digit numbers, no, how did I read this? 6. 5-digit numbers, so 1, 2, 3, 4, 5. Use this, call it the slots method or the, lock method, or anyways. So 5-digit numbers, you can never start with 0. So 10 minus 1, that's 9. So 9 here. Now there are no restrictions. So 10, 10, 10, 10. Keeping in mind from 0 to 9, there are 10 numbers. It's just like how when you flick from page 23 to page 27 in a book, you don't have 4 pages, you have 5 pages, considering the first page or the last page when you don't count them themselves. Same thing. Anyways, 4-digit numbers, so 4 slots once more. Let's erase this 9. Sheesh. Let's erase this 9. This is also unnecessary. Again, 4 more slots for the next one. Divisible by 5, it's always the first number, so either 0 or 5, so 2. And 0 restrictions, but here know that it cannot be 0. Again, keep this in mind. Keep your logic open, so that you always realize if something is possible or not. All digits are distinct, means different. So you can have 9 only, again, 9, always 9 in the beginning, unless they say 0 is a possible number, but when usually we speak about normal numbers, this is not included. The next one cannot be whatever the previous one was, but now it can be a 0. You added one more possibility, but you also diminished one. So same number. Now you diminish, again, one more possibility is you diminish another one, so 7. Just multiply them. This one is just the formula is NPR is n factorial over r, n minus r factorial. And the combination is just n combination r is n factorial over n r factorial times n minus r factorial. And yeah, that's it. Okay, so for this one, for number 7, it says 8, so you basically have 8 people and you want to arrange them in a minibus with 7 seats for the passengers and 1 seat for the driver. So basically 8 seats, 8 people, but 1 is for the driver and the rest for the passengers. Any person can drive, so how do you arrange them? You simply do 8 factorial and that's it. Because anyone, you don't care if there's a passenger seat or a driver's seat, they all combine to be 8 seats and there are 8 people. So how do you arrange 8 things in 8 things? You do 8p8, or more intuitively if you want, you do 8 factorial. You arrange these things wherever they have the place for them. Because it doesn't matter, because you know how you say, how do you arrange books on a shelf? A shelf doesn't really necessarily have a capacity does have a capacity for number of books, but not in the sense that you can only put 7 books. You can put 3, maybe 8 thin books, or 4 big or huge long books. So this is what I mean by the capacity kind of thing. It's not really fixed. So when you say you arrange 8 things, you say 8 factorial. So when you want to arrange these 8 people in any seat in no conditions, so 8 factorial. But if you want to do it how the solution does it a bit more, maybe if you get this a bit more, 8p8. You're arranging 8 things in 8 places, you could say. But in the end, it's going to be 8 factorial over 8 minus 8 factorial, which is 0. 0 factorial is 1. So in the end, it's 8 factorial. Only one way I actually did this, and I got the same answer, is using combination, which is unnecessary, but I just noticed, any person can drive. I'm gonna pick out of those 8 people, 1 person, and he's gonna be in the driver's seat, and the rest are gonna be in the passenger seat. These people, I don't care about their arrangement. 7 factorial. 7 factorial for these people, and 8 choose 1 for this person, because I want to choose someone, and the rest I can arrange them. In actuality, if you do know the formula for a combination, it'll be 8 factorial times 1 factorial times 8 minus 1 factorial, which you'll actually, if you notice, you get 8 factorial over 7 factorial times 7 factorial, you get 8 factorial. You're left with the same exact position you start with, and all of them are the same results. And this is the beauty of probability. It is so strict, so formal, but when you get the idea and you start making possibilities out of it, you can get different ways of solving it. But it can be very rigid, by the way. I myself, sometimes when I did A-level math, and we had the statistics part for some questions before, especially at the beginning of the year and stuff. When I was doing past papers, and it was like I just freeze on the question, be like, how do you do this? I have no idea how to do this. It took me sometimes a while to solve some of them. Sometimes I couldn't even. But anyways, so how many man-woman arrangement? Here you have kind of like a category. You have men and women. Do you care if a man is beside a man and then you flip the two men? Well, you really don't care because you can't make a distinction in this case. So for example, if I told you an arrangement of two men and one woman, it'll be man, man, woman, man, man, woman, man, woman, man, man, woman, man, woman, man, man, woman, man, man. But if you ask yourself, aren't those repetitions of each other? They are, but what I'm doing is I'm flipping those two. I'm flipping those two, flipping those two, flipping, what I'm doing is flipping those two, flipping those two. Anyways, but however, to actually get rid of this repetition, you divide by the number of people in that category that you have, you're using as one entity. So for example, men as one entity. So what you do is 20 factorial over 10 factorial times 10 factorial, which is the same idea for letters. If you've done A-level math, you know this really well, because you've done past papers and stuff. You would see like the letters arrangement, like Mississippi and all those questions. When the letters, you know, repeat and repeat, you divide by the factorial of the number of occurrences for that letter. So yeah, if you have, let's say, another category where you say, I mean, in this case, man, woman. I mean, anyways. Yeah, so pretty much, yeah, basically. So just the number of whatever you like, what you'd expect is like arrange them in 20, you know, they're 20 and you want to arrange them in 20, so 20 factorial over, and then the number of people or number of things in that category. Okay, so for this one, number 9, you just you have like a number of people, 10 people, and 2 of those are the couple and a third person is an old family friend. They just said that just to tell you that, you know, we're gonna giving in context so that you know who are we talking about. So no special request without thinking. Oh no, in this case, yeah, this is important. How are they sitting? The only word that gave this out to me is they said around the table. If it was indeed a rectangular table, technically you can sit around it. I mean, that isn't wrong, but it's just that it's giving me more round vibes, if you get what I mean. So, and since if it's round, it's a rule I myself have forgotten why, but it's 10 minus 1 factorial for round things, round tables and so on. So it's 9 factorial, and so it'll be 9 times, 9 ways. 9 factorial ways. The couple are sitting, they won't sit next to each other, which is reasonable, definitely. So what will happen is basically, it'll be 7 factorial, everyone else is going to be arranged. Use this, by the way, start from 9 factorial, because we already know that it's 10 minus 1. So no need to engage every time minus 1, minus 1. Just keep using 9 as the basic. So 9 factorial, subtract 1, no, actually subtract 2, 7 factorial, and the 2 I subtracted are the couple. So I'm arranging everyone else. The friend and everyone else, I'm arranging them. The couple, however, how do I work with the couple? The couple can be beside each other, right, left, or left, right, which makes a difference because they're different people. So yeah, so you arrange them among themselves, which is 2 factorial or times 2. They're both the same because 2 factorial is 2, or logically you can either have left, right, right, left. So either the what do you call it? The husband on the right and the wife on the left, or the wife on the right and the husband on the left. The couple and the friend are requesting to sit beside each other. Basically what you do for this one is, again, instead of 7 you do 6 factorial this time, and you arrange the 3 among themselves, so you can do 3 factorial, and yeah, that should be basically it. And for this one, just you have 7 blue shirts and 5 red shirts. You want to choose from any color. So they're 12. So 12C, 12C3. You want to pick 3 shirts. They must be of the same color. So either 3 blue or 3 red. So just 7C3, or, which means plus in math or statistics, 5C3. and that's your answer. This one is a bit interesting, but what they tell you is basically a line needs 2 points to become a line, which is, you know, what we know. And however, now we have 19 points. How many lines can we make if no 3 of them are collinear? I mean, we're not really going to consider the collinearity or, you know, the geometric reason behind why can they be non-collinear stuff. So just use the logic. This actually, when I saw the solution, I was like, this is nonsense. Like, I don't get what it means to pick 2 points out of the 19. Like 19C2 is the answer. You pick 2 points out of 19 lines, or 19 points to get a line. But now I got it when I said to get a line. So you basically, how many combinations you can make. So if you have 1, 2, 3, 4, 5, 6, okay, I'm not gonna do all of them. Let's say you have 8 points. How many lines can you make out of this? Ignoring whether they're collinear or not. You can make 1, 2, 3, 4, 5, 6, 7, 8. Basically, you can make 8C2, which, if you're intrigued what that number could be, it's this 6 factorial, so 8 times 7, so it's 8 over 2 equals 28, basically. 28 lines can be made from those. So from this is the idea. You're gonna pick 2 points and you're just make a line. So, and you make combinations, so you use different points every time. So 19C2s. Now I get it why. Natural, this is interesting because when you solve, you're like, okay, so I just use the equation n factorial over 2 factorial times n minus 2 factorial equals 78. And then if you don't know, if you're stuck here, just split this. The n factorial, think of it, 3 factorial is 3 times 2 factorial, which is 3 times 2 times 1 factorial, and so on. So same thing with n. So n times n minus 1, we want to cancel, so let's keep going. N minus 2 factorial. We stop here because we can cancel now. 2 factorial, n minus 2 factorial equals 78. This cancels with this, and the 2 factorial is 2. So if you notice, 2 times this, whatever that number is, it's n times n minus 1. So n squared minus n equals whatever 78 times 2 is. And you get a quadratic formula, you solve. Negatives you ignore, positive you take. And keep in mind, it's a natural number. We are talking about whole numbers. So it must be a natural number. Otherwise, I honestly don't know if you get a decimal, it should be wrong. They will never give you such a thing because it's wrong. Okay, so for this one, we have dice A and dice B. Die A is normal, 1, 2, 3, 4, 5, 6. Die B has 3 ones. It's rigged, basically. 3 ones, 2 twos, and 1 3. This is, the next statement is important, because the first time I read this, I was like, the die is randomly chosen. I didn't pay attention, so I'm like, wait, so are they rolling both die or one die? Both dice or one die? Because in this case, they're only rolling one and it's randomly picked. So in that, when you draw a tree diagram, for me I draw it vertical. You can guys draw it also horizontal. Anyways, I guess maybe horizontal is better in terms of space. Anyways, so we can have die A or die B. Die A has 1, 2, 3, 4, 5, and 6. B has 1, 2, and 3. The probabilities are, well, they're all here 1 over 6, so I'm just gonna write 1 over 6 here. Here for the 3, it's 1 over 6. This one, it's 2 in 6, so 1 over 3, and this one's half, which is why it's rigged. So anyways, getting an even number, probability of getting an even number would be 2. You can either get 2, 4, or 6 from die A, or die B you can get 2. And you just multiply. Probability here is half because it's randomly chosen. So half times, so 0.5, I'm just gonna, I mean, I can do it step by step if you want. 0.5 times 1 over 6 plus 0.5 times another 1 over 6. And there's also 6 here, so 0.5 plus 1 over 6. What I was gonna do is I was gonna show you, like, I was gonna factor it out and just do 1 over 6 plus 1 over 6 plus 1 over 6. Because you can just immediately factor it out, which is half. So 0.5 times 0.5 plus 0.5 times the only one, 1 over 3. And so this is 1 over 4, and this is 1/6, and you just add them, and whatever number you get is the answer. And that is actually used in the next step, because they said that in part B, die A was chosen knowing that the number obtained is even. What's the probability of that, basically? So probability, when you say knowing or given, you immediately think of probability of A given B. So probability of A, die A, given that it's even, the number is even. So that's probability of A intersection even and over probability of even. Usually in this kind of questions, probability of even or whatever the probability of B is, it's calculated in the previous parts. So here we already have this. It's 1/6 plus 1/4, whatever the answer is. Actually, well, I don't have my calculator. Oh no, actually it's there. Anyways, it disappeared. 1/6 plus 1/4, it's 5/12. And so we have 5/12 for this one. The intersection is just pretty much this, A and even. So it's just this, which is half times, yeah, half times half, which is a fourth. So 1/4 over 5/12, which is just flip them. So 12/5 divided by 4. So 3/5. And yeah, pretty much. For this one, we're not going to take much time on it because it's pretty much another application. Number 3 interests us more because it's the game that some of us might have not played as much, or there are some tricks here and there, spades, clubs, aces. So yeah, so number 3 is going to be my main focus in this section. So but let's do number 2 quickly. So we have boys and girls, so easiest section, so boys, girls. And then we have some play chess, some don't play chess, some play chess, some don't play chess. And yes, by the way, the bar is for the opposite, not basically. So we have the tree diagram done, part A. Part B, I mean, we're already going to do it even if they didn't ask. Probability of choosing a boy in the chess club. First of all, what are the probabilities? So 0.45 for boys, 0.55. Playing chess, 15% of the boys and 8% of the girls. Okay, so 0.15, and this one's 0.85. This one's 0.08. Wait, do they play? Yeah, play. And this one's 0.92, pretty much. And so, yeah, a boy in the chess club, 0.15 times 0.45. A student that is not a member of the chess club. Not a member. These people are not members, not members. So it's just that 0.45 times 0.85 plus 0.55 times 0.92. Yeah, and that's pretty much it. The next one is our focus though. So for this one, just a quick overview of, since it's nice, knowing this, because this question might come up, it comes up a lot. So you basically have spades, diamonds, hearts, and spades, hearts, diamonds, and clubs. So yeah, you have four suits as they're listed. Actually, I just noticed. I swear I just noticed. Anyways, as they said, each suit has an ace. I was actually gonna say that. And the rest are like 2, 3, 4, 5, 6, 7, 8, 9. 10, no, 10 is not there, yeah, 9. And then you have king, queen, and joker, or jack. I call it jack. Anyways, joker. So you have 13 basically in each suit. 13 times 4 is 52. So we're picking 4 cards randomly, and what's the probability of getting all 4 aces? Since we're picking 4, so what you do first of all, get the sample space, which you're going to use in all of those parts, which is 52C4. You're always going to divide by this number, whatever it's up there over this. All 4 aces, you want to pick 4 out of those 4, so 4C4. That's for the first one, A. For B, so it's basically 4C4, because you're picking 4 from 4. 2 spades, 2 clubs, so you want to pick 2 from 13, because we just said, each category or each suit has 13 cards, so 13C2 times 13C2. And that's it, over this. And for the next one, at least one ace, you can do the complement. So you basically do, rather than going actually through 4C1, 4C2, 4C3, 4C4 per each, so like 4C4, you want to do 4C1 times whatever is left, so 48C, you know, because you already took 4 aces out. 48C, whatever is left, because you know you want to pick 4, you always want to pick 4. So 1, 3, 2, 2, 3, 1, 4, 0. Rather than doing all of those, because all of those will be at least 1, so basically 4C, 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 like that, and this one will be 48C, 48C. Rather than doing all of those, you can do the complement, but here be careful, the complement is not 1 minus. It doesn't work that way. It's the 1 was probability. Here you're not working with probability yet. To work actually with probability is 1 minus this, which is, if you want to actually, because this is probability, by the way, whatever I put here over this is actually probability. So if you actually want to do 1 minus, you don't do it here, you do it outside. And if you notice mathematically, the 1 becomes magically 52C4, 52C4, because that's how we do, you know, subtraction. We want to get the same denominator, which is what I was going to tell you guys. If you want to subtract, you subtract from the denominator, you call it the, you can call it the, again, the what is this called? Sample space. So 52C4 minus whatever you want to, in this case the complement, which is no spade, no ace. So 4C0 times 48, again we're splitting aces from the rest, C4, because we want to pick 4. This is actually faster than going through them, all of them, and you get the same answer. 4 cards, 1 of each suit, so you either pick no, not either, you will pick 1 spade, 1 club, 1 diamond, and 1 heart. Reminds me of Kingdom Hearts. Anyways, 1 from each suit, so you just basically do 13C1, 13C1, 13C1. Since you're all multiplying them, might as well just cube. But yeah, to the power 4, let me double check something. To the power 4. Okay, yeah, it seems reasonable. Over 52C4. You know, not to waste your time. And then 4 cards of the same suit. So you're basically gonna be like picking. Wait, 4 cards from the same suit. Yeah, so it's just 13C4. Yeah, it's just 13C4 over 52 C4. Pretty much, and that's it. This one's really easy, since you know in all probability distribution tables you just have to have all of those sum up to be 1, because they're probabilities, and all probabilities, you know, of all events will be 1. So it's 2k plus this equals to 1. This will be 3k plus a number equals to a number, so you can solve for this. So let's go to the next one. For the next one, you just simply they give you the formula for finding the probability given the x. So basically, when you have -1, for example, instead of this you have -1, you 0, 1, and 2, and 3. Let me confirm. Oh, okay, this makes sense. Anyways, yeah, so when you have these numbers, so you put -1 inside, you put 0 inside, 1 inside, 2 inside, 3 inside, you get the probabilities. Now, the only thing you don't know is b. You replace x. What you do is the same thing as the previous one, you just add them up. This plus this plus this, and all in a table, and you just equate to 1. And that's how we solve for b, because you only have one unknown. And that's it pretty much. Here they said put it in a tabular form, just put the probability under the x, and yeah, pretty much. Anyways, these should be easy. They slowly start to get more technical. So for this one, you just need to notice, all of us would really see it, I don't think. Anyways, it's just nice to, point it out, is that here x is the number of red balls, and you have 3 and you're gonna pick 5. So you'll end up having an x where you stop, which is the maximum number of red balls, which is 3. So you can go 0, 1, 2, 0, 1, 2, 3. And just put the probability under, which is, for 0 means 0 red balls, which mean all from black. So C, 6C5. The next one is 1 red ball, so 3C1 times 6C4. And then the next one, 2, is 2 red balls, so 3C2 times 5C, 5C2. No, we want 5, right? So 3. And then 3, same thing, so 3C3 times 5C2, and so on. And that'll be basically your table. Yeah. Combination techniques found. Yeah, so we found the possible values up, and we found the distribution here. The expected and comment on the answer. So we want to find the expected. The expected, you just multiply x by probability and then you add them up. So summation of x times probability. So 0 times this 0, this times this is 5 over 32, plus this times this is 10 over 16, this times this is 10 over, I'm just going to write without simplifying, 30 over 32 plus 4, 20 over 32 plus 5 over 32. And you just add them up and this will be your expected. Comment on the answer obtained. Say you get some number 2.3, some random number. Actually I can calculate, but I'm too lazy. Anyways, so 2.3, if you get 2.3, how do you comment on this? This is, I mean, statistics AP people know this. So if you want to comment, you'd be like, on average, you'd have, what is X, first of all? We're tossing a coin 5 times the number of heads. So there, on average, there'd be 2.3 with repeated, you know, AP stats people have more, you know, detail to mention. But this is, again, this is what I recall from last year, because I did it last year. You'd say something like, on average, with repeated trials and so on, you'd have on average, you know, 2.3 heads occurring in when a coin is tossed 5 times, something like that. And the last one is find variance. Variance is it the same table? No, it's not the same table. Variance is special. Variance needs more attention, and it's like the longest thing you can do, which is still short, but it's, you know, the longest. Basically, I'm saying it's all easy, by the way. So variance is basically you know how we do for the expected x times probability? This time you'll do x squared times probability, so x squared. So summation, if you want me to write the formula thing, which I'm coming up, by the way, on the spot, like I'm writing them on the spot. I haven't memorized anything. I always remember it's just x squared times probability minus expected squared. So x squared times probability, so times, I'm just going to write p, minus the expected squared. So square inside, square outside. So again, I asked for if it's a new table, because if it's old one, we could have just used the expected above. Anyways, I'm not gonna do the calculations, but just x squared. So you know, 4 times 0.25 plus or minus, because, you know, minus, no, it's getting squared the other way. So plus 0.25 times 1, because, you know, squared, plus 1 squared again times 0.25, 2 squared, so 4 times 0.25, minus the expected, which is this times this plus this times this, and, you know, it's calculator work. So the expected square, I'm just going to keep it like this, and yeah, you find it. Variance must always be positive. Keep that in mind. Variance must always be positive. It's a square of the standard deviation. It must always be positive. So keep that in mind. So for section 8, for this part, we're just gonna be talking about the, I guess, the shifts and stuff, because this is actually can be explained as a shift, and this one is pretty similar. It's more like a stretch. Anyways, you have a fair die, so 1, 2, 3, 4, 5, 6. Each one has a probability of 1/6 because it's fair. Expected value, immediately the average, because you do know that, by the way, the expected value is the weighted average. This is another way to say it. Why am I focusing on the word weighted? Is because if there are different probabilities, like this one's, they're all the same, but the previous one, I think they had all different. Yeah, here they had different probabilities. It's weighted because there is a weight for each number. Like this has more emphasis and this has more emphasis than these two. So it's more like a distribution. You can think of it like this for this one. This one has so much weight and so much consideration. This one is barely even considered. So it's pretty similar here. But here they all have the same weight. So you can just do plainly the average. Or if you know it's 3.5 already. But if you want to do it, you just do 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. You get 7/2. Which is, by the way, the same as what they wrote. What they wrote was unsimplified. The unsimplified version, which is 1, 2 plus 3, blah, blah, you get 21/6, which is the same thing as 7/2. That's expected. Variance, now this is where you have to do the work. Oh, where was I looking? It's here. Anyways, still, you have to do the work, so it's going to be 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6. You add them up, minus the expected, because 3.5, so 3.5 squared. you get the variance. Again, make sure it's positive. It must be. This one you just add, you're rolling twice and you're just adding x1, x2. And so basically what you do is for the it's just expected plus expected, variance is variance plus variance. And they're exactly the same, by the way. X and x1, x2 are just fair die, you're just rolling twice. So one is the first try and the second is the second roll. So you just add variances, add expected values, and just you get the new ones. Z is you're multiplying the score by 10 times. So if you get a 6, it becomes a 60. If you get a 4, it's a 40. So you multiply the expected by 10. Makes sense. Variance, on the other hand, it gets a bit more complicated, because you remember how we say we do x squared times probability? This is why when you take in variance of, so it's 10x, right? It's 10 times x. 10 times, yeah, 10 times x. So it's going to become 10 squared times variance of x when you take it outside. I just wanted to confirm this. So yeah, that's how we basically do it. With variance, when you want to take out a number, you want to square it. For this one, you just need to do some manipulations. Again, we're going to rely on formulas and stuff. Yeah, so find m if expected of 2x minus my is 0. So basically, you just split them, so it'll be expected of 2x minus expected of my. The m can be taken outside, the 2 can be taken outside, like this. And this is equal to 0, and this is how we can solve for m. You take this to the other side, divide by the expected of y, and you get 2e expected of x over e expected of y, and sheesh, what a timing. Anyways, yeah, and yeah, just divide pretty much. For number 2, you just take them out, factor. So e of 2x, expected of 2x minus expected of m times y, the variable y and variable x. You can take out 2, take out m because they're constants. So 2m, expected doesn't really square or anything, so you can take it out, equals to 0. You can solve for this, take this term on the other side and divide by expected of y. You'll get m equals 2e expected of x over e, or expected as in, of y. And you get m. This one, find e of x squared. Remember, variance, we have the variance. So variance of y is expected of x squared, which is, by the way, the same as what I have drawn. If you've seen the previous question, me solving it, it'll be expected, summation of x squared times probability, which is, by the way, if this is taken to be a big X, it is x times p, summation of xp, which is expected of x, but not any x, it's x squared. So summation, so basically variance of y is expected of x squared, this is squared, looks like x to the x. And let me fix that. Anyways, so expected of x squared minus expected of x, all of it squared. If you, not to get confused. So you can take this on the other side. No, you will want this, right? Yeah, so take this on the other side. So it'll be this plus this. So let me show you. Expect x squared equals to variance of y plus expected of x, all of it squared. And that's how you actually get it in the solution, like they just jump to it. Variance of y, we have 1.2, expected of x squared, where is it? Expected of x is here 2, so it'll be 2 squared, so it'll be 4. And yeah, pretty much. No, wait, are we working with, yeah, x, yeah. I wrote y, I don't know why. I wrote y, I don't know why. Anyways, find real numbers, blah, blah. Okay, this one's a bit annoying because it's linear combination or substitution, or, you're solving two variables, or two unknowns, two equations, two unknowns. So this one, again, nothing special, take out. So a, what do I keep writing summation? I mean, summation here was right, but here it's wrong. Anyways, expected of x plus b expected of y. It's hard to talk and write, actually. not without making mistakes. A squared, if you take out for the variance of x, plus b squared variance of y equals to 3.2. And you just do combination, you substitute this, and this, so that you actually have values to work with. And then you do a equals whatever, you know, b is, so that you can substitute b in a, and then you get b squared, so you can solve for b, and then you substitute back for a. And that's pretty much it. And on to the next section. So for this one, k, you just add them up. This plus this plus this plus this equals to 1. So you're gonna get 6k plus 0. Man, I need to fix the k's, they're hard. Plus 0.4 equals to 1, so it'll be 6k equals to 0.6, and so k equals to 0.1 because you divide. Evaluate. F is what? Cumulative distribution. So you want to put 0, 4.5, and 10. This one actually threw me off guard because 10, there's no 10. It stops at here, and this is where the summation for F is 1. So I guess, you know, it's anything above that is gonna be 1, because, you know, you cannot have anything above the summation. So 10, 100, million, 1,000, 6 billion, whatever, it's gonna be always 1. It's different for all graphs, by the way. Some graphs actually have numbers, not probability. So you might have 400, might have something, but it should stop at that point. So if it's 400, it's gonna stop at 400 and so on. So for this one, it's going to be less than or equal to for all of them. So less than or equal to 0, less than or equal to 4.5, less than or equal to 10. Less than or equal to 0, nothing before 0. At 0, there's 0.2 because, you know, k is 0.1. So it's going to be the answer for this one, 0.2. For 4.5, there is nothing on it, but there's before it. There are 3 of them, and the summation is 0.8. 0.2 plus 0.3 plus 0.3 is 0.8, so 0.8. Less than everything before 10, I mean, if it finishes at 8, so you don't even need to calculate. It's immediately whatever is the summation of them. Knowing that it's probability, the summation is 1, so it's 1. Or you can work it out by adding, which is the same thing, by the way. F is a piecewise function, and you just make it like basically write it as. So you want to always start with 0. Since we said that it's less than or equal to 0, it's 0.2, we cannot do this and say this is 0, because it's a contradiction. So if we actually want to start from 0, you just don't include the 0. And since we don't include, we are gonna start between values. So we're gonna include it and anything above it. So we're gonna be like this, basically. 0, exclude, include, exclude, include. We're starting from 0, and this is like the 0 mark. Anything before 0 is 0. Anything on 0 is this and above, and so on. This is actually how you graph the function, and it keeps going. So this one is 0.2, this one is 0.5, 0.8. Again, don't forget it's cumulative, so you can add them up. 0 and between 0 and 2. Don't put equal because you can put it in the next one. So 2 less than or equal to x less than 4. I want to put 3 so badly, I don't know why. 4 less than or equal to x less than 6. 6 less than or equal to x less than 8. And we're done basically. Or actually, no. Actually, since we've gotten a 10, I don't know what the solution says, but we can basically place x greater than or equal to 6. This actually includes, no, not 6, 8. Wait, what? Oh, never mind, there's no 6. This is 8, and this is 8. Yeah, so now it makes sense. I'm like, wait, it doesn't work with the 10. So anyways, now we included everything, and this is the piecewise and how we graph it, like how I've done above. And so for this one, it's just that draw a histogram. This is, since it's probability, we don't need this, what do you call it? No, we can use frequency density, but they're all uniform. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's not 1, 5, 7. You know, it's uniform in intervals. So since it's uniform in intervals, they have equal intervals. You can just use the probability for its, you know, immediately. 0.2, 0.2, they all have the same height. They're all the same. They basically just look like one rectangular block that has been cut up into 5 pieces. So anyways, so how do you comment on this? It's uniform. It's a uniform distribution, pretty much. It's uniform. Same thing throughout, and, you know, just uniform. So yeah. Hello everyone, once again. I'd just like to say a few things. So first, I'll start with thanking everyone for being really nice people, for supporting us throughout. Your nice comments are what made us keep going with these videos. Making them took time, editing them took time, and making the website itself took time. So sometimes some of us had to stay up night, whether it be recording, editing, or even just making coding on the website, or fixing things, or getting the URL in the first time to work. Yeah, I still remember that. Anyways, but you guys have been supportive throughout, and it's just not just that. It's been throughout the year. You guys have been really nice people, and I've had some really nice memories here. Mostly, what keeps me, I think some of us like agree on this, is that what really is nice about the memories we had in this school is us. Us and some of our teachers and so on. It's not really the system or anything, but it's our memories together. It's what we have done together. I still remember these times when we used to be in the SLO and we do things. So, anyways, some of us are getting emotional, but anyways, I still remember that. Yeah. So I just like to thank everyone and congratulate everyone, by the way, for going to the universities they want, or maybe not the one they want, but it's still maybe either a safe university or some other second choice, or maybe they have a few choices and they're worried. But I just like to congratulate everyone and say that no need to be afraid, do not worry. Even if you don't get into a university you wanted, or it's been really tough, or you're still worried about the visa, or some of you are going to America, say the green card or something, or many other cases, the rent, the life, the people, the changing cultures, the difference, anything out there. Language barriers, for those who are starting to learn certain languages, no need to worry, just take it easy, step by step. You still have a life ahead of you. This is nothing but a quarter of your life, and it's one stone, one keystone, this one huge step you'll be taking, and you passed it. All of us passed it, no exception. And so the last advice I'd like to give, maybe, I guess, is that enjoy life, because it's with you and you're gonna be years and years and years. So might as well just enjoy it, because otherwise you're gonna go from studying in college to working to having a family, for those who will be having a family. And yeah, so it's gonna be continuous list of events. It's gonna be a sequence, and if you just keep running after everything, and this is again advice to myself also, but when I advise someone, usually I listen to it better than if I knew this and just buried it in my mind. So yeah, so I'd like to say enjoy life, do things that you like. For me, I'm planning on traveling, seeing around the world, but maybe before that, securing some kind of stable income or something that you can have, and then from there expand, maybe learn new skills, see the world, meet people from do the things that I couldn't do years ago, and so on. So maybe change things in myself, try new things, meditate, yoga. So yeah, so I just hope for everyone to have a nice happy life, to lead, for those who are gonna have family, lead a happy life with their family, make some sweet memories. And yeah, thanks again and congratulations. See you hopefully in the future one day. So take care, guys.